this is the next video in a playlist that I'm calling General Linear Models Design of Experiments. And this is part 6 in a little mini series that I'm calling the Regression Approach to ANOVA. And essentially we look at the reduction in the sum of squares when a term is added to a model containing other terms. And I'd really encourage you to watch the first 5 parts. But in this video we're going to illustrate those ideas. Now here, this is made up data. It's 3-way ANOVA data. Looks like this. So this would be the response, treatment A, treatment B, treatment C, or factor A, B, C. And if we look at the ANOVA, so this is the M stands for model, and then the A is what terms are in the model. So MA. And if we look at the summary, so we have a sum of squares residual, sum of squares due to factor A. If we look at the model with B plus A in it, and I put it this way because in R they use type 1 sums of squares where it's model dependent. And so what it does is it calculates the sum of squares, the reduction in the sum of squares when B is added to the model when just the mu parameter is added. And then the next term is, it's the reduction in sum of squares when A is added to a model with B already in it. And if we look here, look at the sum of squares for A. Remember, this is type 1, so it's conditioned on or adjusted for factor B. And this one here is not conditioned on B. It's just the reduction in sum of squares for A. And notice they're the same. And the reason is it's a balanced design, and we can orthogonalize all the columns of that design matrix associated with each of these, factors or treatments. Now the ANOVA does exactly what this little mini series is saying. It looks at the reduction in the sum of squares there. So here we compare model MA, which is the first one, to MAB, which is the second one here. So it takes the sum of squares there, which is this, 234, right? Compares it with the residual, the sum of squares there, for this fuller model, which is 213.5, right? Looks at the reduction, and it's 20.5, or 20.25, and then it calculates, of course, a p-value associated with that. Now, but notice that all of these are orthogonal. So there's a 900, there's 900, there's 20.2, this is 20.2. The reduction in, the difference of the residuals is actually just sum of squares for B. Now, if we look at a model that has A in it first and then B, notice that the sums of squares are the same, even though these are specifically type 1 sums of squares. They're the same. Now, let's do models with 3 components. So the first one is MBC, and the next one is MABC. And if we look at the reduction in the sum of squares when A is out of the model compared to B, that's what this ANOVA command does. So if we look at this, so that's 2607, the residual 1707, and that difference is 900. Well, that's exactly what the type 1 sums of squares is right here, 900. And the reason, it's a balanced design. So all of these type 1 sums of squares, type 2, type 3, type 4 are all equal in these balanced designs. Notice the 20.25, 20.25. C is 36025, 36025. The 900 is actually incorporated into the residuals, when we compare these two models. Now, if we look at MBAC and MCBA, meaning we just add the terms in different orders, notice that the sums of squares are actually still the same. Now, this one here, since these are type 1 sums of squares, this particular one is the reduction in the error sum of squares, sum squared error, when A is out of the model, when BC is already in it. So this is a type 3 sum of squares. But notice that it's equal to this right here, this type 1 sum of squares. I mean, they're all equal because it's orthogonal. I guess that's really the driving point that I want to prove. Now, there is a little complication when we enter in an interaction term, when we add an interaction term to the model. So let's look at model 1, where it's just the constant term, the mean, and then we just have the A treatment in it. Notice it's the same. It's 900 in all of these because it's orthogonal. That's the key thing. Now, model 3 here has no A term, has B and then the interaction term. And then model 4 has all the terms, A, B, and the interaction term. But notice that B is 20, 25, 20, 25. The 900, the interaction term actually is if we look at the previous, the interaction term actually encompasses the factor A, right? So 1800, that's really 900 plus 900. And these are all orthogonal. But when you have a balanced design in an interaction term, the perpendicular projection matrix on the whole column space is actually equal to the perpendicular projection matrix onto that subspace. So they're actually equal. And I think in 1, 2, 3 little mini series from now, we'll talk about interaction terms and calculating the perpendicular projection matrices, etc. But a couple of notes that I wanted to point out is if we look at the sum of squares residual, sum of squares error, notice that it's 1113, and this is without the term A. And we add the term A, and the residuals is the same, right? Because if we look at the quadratic form of that sum of squares error, it's y transpose I minus m y, and m is the perpendicular projection matrix on the column space of X, but the perpendicular projection matrix are the same as for the interaction term. Anyway, so I'm being a little vague because we haven't covered this in the little mini series yet. But if we look at mod 3 minus mod 4, it's actually 0. It can't be. There's no reduction in the sum of squares error in the residual term, right? Depending on these models. So you can't, it doesn't make sense to do it like that. Now, mod 1, 2, and 4, I just want to show you that we can do that. So it takes, the sum of squares error for the first model, sum of squares for this second model, subtracts them, you get 900, and we can calculate an F test statistic, a partial F test. And here, the mod 4, we've added A. We've added B and then that interaction term. And we can still calculate the reduction in the sum of squares error, and then use that partial F test. Okay, well, that's all I have for this video. Hopefully you enjoyed that and it drove some points home about this type 1, 2, 3, and 4 sums of squares. And the next little mini series, we're going to look at incomplete block designs. So hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.